Came up with a way to figure out areas. Let's stop talking, guys. Find out areas of similar shapes. So we want to do something similar, no pun intended, with solids. So we're going to talk about area and volume ratios. For similar solids. So let's remember how we decided if things were similar. What our everyday definition? What has to be true about our shapes for them to be similar? So you're right. Let's just back up an even bigger picture than that. So we're going to get to that detail. So keep that. You're right. I just want a bigger picture. What do they have to be? For shapes to be similar, can a cone be similar to a sphere?
No, they have to be the same shape.
There we go. Similar shapes. We said they are the same shape. And then Danny also said we're going to say corresponding dimensions are proportional. And I say corresponding dimensions because we could say corresponding heights, corresponding slant heights, corresponding radii, corresponding circumferences. So we can compare anything that's the same between the shapes, and those are proportional. And proportional means they are. You said something about ratios? Same ratio. There we go. Proportional means the same ratio. Same. So we figured out if things were proportional by making ratios of the corresponding parts and seeing if they're the same. So let's look at an example here. What if I had a shape like this? What kind of shape is that? Rectangular prism. If all the dimensions were exactly the same, we could say it was a cube. But a cube is also a rectangular prism. And what's our everyday term for a rectangular prism? It's a box. All right, and there are the dimensions of these two rectangular prisms. And the question asks us, are they similar? So we need to make ratios to decide. So what side are we going to make a ratio with 8? 8 over 10. And we can reduce that to 4/5. All right, and what ratio are we going to make with, what side are we going to put with the 3? 3 over 4. Are those the same? No, these are not the same. So they're not similar. All of our corresponding ratios would have to be exactly the same in order for these to be similar. So all of them would have to be 4/5, or all of them would have to be 3/4 when we made those ratios in order for it to be similar. That's how we decide if something's similar. If the two shapes are similar, do you remember what we called this ratio of the corresponding sides? The scale factor. That ratio, if they're similar, that ratio is the scale factor. All right. So let's get to the important part of what we want to talk about today, our areas and volumes. If the scale factor and the scale factor, the other way we thought of the scale factor was a length ratio. And the reason I write length ratio could be the ratio of the heights, the ratio of the slant heights, the ratio of the perimeters, the ratio of the, what else could it be? The ratio of the radii, some length ratio. If the scale factor is A over B, then the ratio of areas is, and we did this in the last chapter. What do we do to the ratio of the scale factor to get the ratio of the areas? What are the units for length versus the units for area?
Oh,
Meters and meters squared. We square it. Is A squared over B squared. We square the length ratio to get the area ratio. We did this in the last section. The ratio of volumes is, think of our units for length and our units for volume, meters and meters cubed. So the ratio of the volumes is going to be A cubed over B cubed. We cube the length ratio, the scale factor, to get the volume ratio. And we're going to use these ratios to solve problems. So we square the length ratio to get the area ratio. We cube the length ratio to get the volume ratio. And the area ratio could be the surface area, could be the base area, could be the lateral area. Any area ratio is going to be the square of the length ratio, and then cube it to get the volume ratio. All right, questions there? And it helps to remember about the units. Meters, area is square meters, volume is cubic meters. Square, cube. All right, let's take a look at a problem. The volumes of two similar solids. Are 40 cubic inches and 135 cubic inches. The surface area of the smaller is 48 square inches. What is the surface area of the larger? So there's our question, there's our problem. Well, what piece of information does the problem give us? We know the surface area of 1, and we know the volumes of 2. So what can we do with these two volumes?
Would you like put them into the ratio and like one would have an X to it?
Okay, so what Danny's saying is part of what we're going to end up doing is setting up a proportion where that missing surface area is the part that we're trying to solve for. What ratio is this? What ratio is this? Are these two numbers? Or what ratio is these two numbers going to give us? This is going to give us the volume ratio. Our volume ratio, and since we're looking for the surface area of the larger, I'm going to do larger to the smaller. The volume ratio is 135 over 40. What are we going to do to the volume ratio? Or let me rephrase that. What relationship do we know that has to do with the volume ratio? We know how to get what from the volume ratio? Let's go back here. The volume ratio is related to the length ratio. So the volume ratio is A cubed over B cubed. Whoops, went the wrong way. That is A cubed over B cubed. How do we get back to the length ratio from this? How do we undo this cube? Cube root. So let me write our plan out here. So we're going to, step 1, use volume ratio to find the length ratio. Since the question asks us about surface area, we're going to use the length ratio to find the area ratio. So this is our plan here. And then 3, we know ultimately that we're going to set up a proportion to find the area. So to get back to our length ratio here, we decided we're going to cube root. And so when I take the cube root, I get the length ratio. And when we do the cube root of this, we can just do the cube root of 135, put that on the top, and the cube root of 40, and put that on the bottom. So when I plug this into my calculator, I get 5.13, cube root of 135, over 3.42. That's the cube root of 40. So I just did the cube root of this one divided by the cube root of that one. So that's our first step. There's this. Use the volume ratio to find the length ratio. Now with our second step, we are going to use the length ratio to find the area ratio. What do we do to the length ratio to get the area ratio? What is it? Square it. So the area ratio equals 5.13 squared over 3.42 squared. So I plug that in my calculator and I get 26.32 over 11.7. So there's my second step. And now we're going to set up a proportion. The area ratio, 26.32 over 11.7. We're trying to find the surface area of the larger. So what are we going to call that? X. What's the other area that we can put in the bottom there? Surface area of the smaller is 48. There's another area ratio, x over 48. We don't know this area, but we know this one. These two area ratios have to be the same because we're talking about the same shape. We did some problems like this in the last chapter. Now how do we get x? How do we solve for x? And since x is on the top, all we have to do is multiply both sides by 48. Those cancel, just leave me with 1. And I plug this in my calculator. X equals 48 times 26.32 divided by 11.7. And I get 108 square inches. What would happen if the area of my larger one was smaller than the area of the smaller one? That means you made a mistake. Better turn out larger, right? All right, questions? Questions there? Okay, let's go through that process one more time, slightly different kind of problem, just so we see the thinking behind that kind of problem again. All right. And then we'll be done. So for this one, the surface areas of similar solids are 52 square feet and 208 square feet. The volume of the larger is 192 cubic feet. What is the volume of the smaller? So very, very similar kind of problem here. So anybody have how are we going to set this one up? What ratio can we write with the information that the problem gives us? Well, we can make a ratio with the 208 and the 52. What ratio would that give us? Length, area, or volume? Area. That would give us an area ratio. So we can say the area ratio equals, and since we're looking for the volume of the smaller, I'm going to do smaller to larger, over 208. Our area ratio is 52 over 208. We want to get to the volume ratio. But what gives us our volume ratio? The cube of the length ratio. We're going all the way back to the length.
Square root that and cube it.
So we're going to square root this. So let's write our plan over here like we did before. So we're going to use the area ratio to find length ratio. And we decided we're going to do that by the square root. We take the square root. So we're a little ahead of where we were last time, because we know what we're going to do. Use length ratio to find the volume ratio. And what did we decide we're going to do to find the volume ratio? Well, we're going to find the length ratio by doing the square root. Once we have the length ratio, how do we get to the volume ratio? Cube. We're going to cube it. And then finally, we have to have something to do with our x, so we're going to write a proportion. So we're going to take the square root of the area ratio. So the length ratio, I'm just going to take the square root of 52 and divide it by the square root of 208. So I'm going to write that as 7.21 over 14.42. That's I just took the square root of the top and the square root of the bottom. So there's our first step. Use the length ratio to find the volume ratio, and we decided we were going to cube it. So the volume ratio (7.21) cubed over 14.42 cubed. Plug that in my calculator, and I get the volume ratio equals turns out to be, when I do this and I reduce the fraction, turns out to be 1/8. So that's the second step. And then I'm going to finally write a proportion. So here's the volume ratio, 1/8. And that's going to equal, what's the other fraction we're going to use? Volume of the smaller is what we're looking for. What do we call that? X over 192. And to solve this, I'm just going to multiply both sides by 192 and make this arrow shorter. And x equals 24 cubic feet. Mm-hmm.
So I'm confused on even like cubed 7.21.
We did. So when I cube 7.21 and over 14.42 cubed, it reduces. I get a fraction that reduces to 1/8. So I just reduced the fraction. You could use the numbers that you got, and you'd come up with the same answer. Okay. All right. Questions? Okay. Homework.